All right, guys. So thanks for submitting the polls. So I'll just announce the results. So 88% of today's audience is mechanical engineering, which is great. And 91% of today's audience are basically beginners. So that's around 130, 140 students. And I see that there are 2 to 3 people who have filled out that they are actually advanced ML and AI users. So I would like to point out that this is going to be an introductory level webinar. So guys who are fairly advanced, you might still be able to learn a thing or two from this webinar, but this webinar is primarily oriented or intended for people who have no prior experience with ML and AI. However, this is a series of webinars, so we will have sessions where we discuss intermediary and advanced topics. Okay, so I think the time is.
Yeah, Sarang, the time is 6:01. You can. I probably think you can start the workshop now.
Great, thank you so much.
Yeah, thank you, sir.
All right, guys. Like I said, once again, thank you all for taking the time out of your busy Saturday evenings to attend this session. We really appreciate it. So before we get started, I just wanted to, take a couple of questions that we all commonly get and answer it. So how long is the session going to be? Well, it depends. There is a demo that has been planned. So it's going to take anywhere between 40 minutes and 1 hour. This webinar is also being recorded. So there is no reason for you to record this webinar. And the recording will be shared on our YouTube channel for free in the next 1 to 2 days. All right. So it would be really great if we don't get the exact same questions again in the chat window. As you can all see, there are 200 plus participants. It's going to be very hard for me to read the chat instantaneously while also presenting. However, I will try my level best to answer questions on the fly. If not, I can try to do a small Q&A at the end of the webinar to answer most of the questions. So that being said, this is an introductory webinar. Majority of today's audience is mechanical engineering students. So we will primarily answer the fundamental question, what is machine learning and artificial intelligence? And I will try my best to not give you another textbook answer. By the end of today's session, you will have a decent understanding of what machine learning and artificial intelligence is. And I will hopefully be able to give you some intuition on how ML and AI can be used, say, in your field of study. If you're a student interested in thermal engineering, or if you're a student who is interested in fluid mechanics, manufacturing, hopefully by the end of today's session, you will have at least 1 or 2 ideas on how you can actually use machine learning techniques in those type of applications or projects. So an important thing is to kind of understand the historical background of ML and AI. I think it's very important. This is something that especially the guys with intermediary level expertise will appreciate. So then we'll directly talk about the fundamentals of the subject. So here, the main thing that you need to get used to is terminology, right? And a lot of fundamental mathematical concepts. So I'm not going to be defining all the concepts that you need to kind of understand that. Understand ML and AI completely. That is basically what we teach in our course. But I'm going to kind of give you a generic introduction or a generic intuition, which will help you understand the uses of these math concepts. So then we will obviously look at a cool examples of ML and AI. And I've actually planned a demo on MATLAB, where I'm thinking of showing a live example of an image classifier that I've written based upon AlexNet. All right, so let's start with ML and AI. Intelligence and for machine learning, there's no clarity can record on that front. So in general, artificial intelligence or in general, machine learning is actually a set or is actually a subset of artificial intelligence. See, artificial intelligence is basically using your computers to do intelligent tasks that typically only a human being could do. Example, playing chess or driving a car, right? So that is what you would call as artificial intelligence. Machine learning, it is a subset of artificial intelligence. So in machine learning, the idea is very simple. You're training a computer, right? You're training a computer to solve problems, and then you will test the computer to see if it has actually trained properly. A great analogy is you going to an engineering college. So majority of the main reason why all of you enrolled in an engineering college is fairly simple, right? It's to learn engineering, correct? And if you look at the college, what does it do? It trains you and then it tests you. The only bad thing is in most engineering college, the test is an exam, which is not a bulletproof test, or it's not a aggressive test to test someone's knowledge in engineering. You're just testing someone's you're just testing the capacity of a person to mug up or memorize details, right? That doesn't work. But that is exactly what machine learning is. In machine learning, you actually have to train your computer to understand a particular problem and then see if it actually solves very well. Just like a poor engineering college, if you train your machine learning model very badly, it's going to give you garbage results, right? So always remember the thing, garbage in, garbage out. If you feed in garbage input to your machine learning model or even to your brain, for example, it's going to be garbage out at the end of the day, correct? So that is kind of the differentiation between machine learning and artificial intelligence. So when people are talking about data science, people are talking about artificial neural network, convolutional neural network, they are in general 90-95% of the time talking about machine learning. Okay, so that is something that you need to understand. Artificial intelligence, like I said, is the larger set. Machine learning is the subset that people care about these days. Okay, now let's think about how do machines learn. There's a typo there, it should be machines, but it's very simple. Most of you have taken some form of engineering mathematics course, I assume, correct? You can just type in yes in the comment section if you have taken any mathematical course. Okay, thank you, Arth. Thank you, Gautam. Great. So if you consider a mathematical course, there is always the concept of functions. Or for example, when we say y is equal to f of x is basically called as the inputs to the function and y is called as the output, correct? Now let me ask some very simple dumb questions. How many inputs can a function have? Is there a limit to the number of inputs that a function can have? Right? In general, no, correct? There are no limits to the number of inputs. What about output? Can a function have multiple outputs? The answer would again be yes, right? So you can have multiple inputs and multiple outputs. In fact, that is a very nice way to think about a function, because it helps you understand that, okay, it can give you multiple inputs and multiple outputs. Now, mathematically, when you have taken M1, M2, or M3, you're usually given the function. For example, if I say that the function is y is equal to x square, y is equal to x square, that's the equation of a parabola, right? So now if x is equal to 2, what is y equal to? Exactly, right? Fairly simple. If I've given you the function, and now with this function, you're able to calculate the output provided I give you an input. Now machine learning, it just works the opposite way. I will give you an input and output. Now you need to figure out what the function is. So let's just go through a simple example. I'll say that y is equal to 27 and x is equal to 3. Can anyone figure out what the function is? Y is 27 and x is 3. Exactly, right? Now, what would you do if I also say that, y is equal to 25 and x is equal to 4? Right? You can still calculate, right? You can still calculate it, but here's the thing. What if I tell you that both the inputs and outputs that I gave you are valid? Meaning, when x is equal to 3, y is 27. When x is equal to 4 or whatever I said, I forgot, y is equal to 25, right? When I basically give you both these two inputs and both these outputs, in other words, I give you a set of inputs or a set of outputs, then figuring out f becomes a bit more of a challenge, correct? And that is what machine learning deals with. So usually the number of inputs that you have, you're not giving 1 or 2 inputs. If you're just giving 1 or 2 inputs, you really don't need machine learning. You can just do curve fits and get away with it. You're dealing with, say, 10 or 20 inputs. And with respect to outputs, you're looking at, again, this is where things can get a bit tricky, but you can have 1,000 outputs, right? So this is where the concept of matrices come in. Especially in the world of machine learning, you basically provide an input vector, or which could be a row matrix or a column matrix, and also an output vector, right? And then your machine learning model has to compute the function f, which will basically give you this y output for a given input. Now, let me ask you this question. Do you think it's going to be very accurate? No, right? But you know, when we're talking about engineering, I cannot say that I cannot go and perform engineering calculations by measuring accuracies by measuring accuracies using English words. If I say that accuracy is less and accuracy is more, that is relative, correct? So mathematically, you have to figure out a way to represent your accuracy in terms of a number. And this is what you call as a cost function. Right, this is a very important terminology that you learn when you jump into machine learning, right? So cost function. So far, what have we discussed? We have discussed that x and y are inputs. These inputs are usually matrices because you don't have a single input. You have lots of inputs. It can be a row matrix or a column matrix. And then we know that there is something called as cost function, right? We have something called as cost function, which helps you understand how your predictions are with respect to the provided data. Okay, so then there is this concept of artificial neurons, right? So whenever you hear the term machine learning, you basically hear the term artificial neural network that goes along with it. So what are these artificial neurons? Well, to start with, artificial neurons are basically inspired from a real neuron. A biological neuron is something that everyone has. We have billions of neurons in our brain. So what does the neuron do? Well, I don't want to make this into a biology class, and also I don't know a lot about biological neurons. So to keep it simple, on the left-hand side, you have your dendrites, which is basically an input. Your neurons take inputs, and then on the right-hand side, where you have your axon terminals, that's where the output actually comes, right? So your single neuron is basically like a mathematical function. Y is equal to f of x. X is the input that comes through the dendrites, and your neuron does something, right? It does some calculations, and then it produces a y on the right hand side, right? So this is essentially a y equal to f of x unit. With respect to that function f, a biological neuron obviously performs a lot more calculations than an artificial neuron. Now, if you take this inspiration and try to draw a neuron, which I've done here, this is what you call as an artificial neuron. Traditionally, or if you look at any textbooks, it's not presented this way. The input lines are basically lines; they're straight lines. So I've just modeled them as curves here, so that I can kind of show that okay, this is very similar to the image that we saw before. But here I have two inputs and I have two outputs. Okay, so I'm going to introduce some very small notations. I1 is your first input. Okay, I1 is 5, and I2 is your second input, which is equal to 2. And this right here, you can see that this input line is thinner than this input line, right? I'm kind of using this visual representation to explain to you guys the importance of those two inputs, right? So here I have two inputs, 5 and 2, right? What those inputs are, it could be anything, right? Let's not worry about it. The first input, we are giving it a very small weightage. We are saying that W1, the weightage for it is just 1. And the second input, I2, the weightage for it is 12. In other words, I2 will get multiplied 12 times, whereas I1 is getting multiplied only 5 times. And I have two outputs here. The first output is basically summation of products of inputs and weights. And the second output, which should be O2, sorry, not O1, it's nothing but the subtraction of the products of input and weight products. Okay. So now what's going to be O1 and O2? Can anyone do the calculation very simply? What is O1 and what is O2? And if you're confused, this is O1 and this is O2. Okay, O1 is 29, all right. What about O2? Exactly, right? So O1 is 29 and O2 is minus 19. And this right here, this formula that we have, that we use to compute your outputs is called as your activation functions, right? This activation function is something that I'm saying, right? I'm saying that is what this neuron does. And if you do it, if you did the math correctly, O1 is going to be 29 and O2 is going to be minus 19. Now let me ask a very simple question here, guys. Now, if we go back to a couple of slides back where we talked about the essence of machine learning, the primary concept that a machine learning model tries to capture is the relationship between input and output, correct? So is my output value known or unknown? Can anyone tell me in the comment section? Is my output value known or unknown? My output value is known, great. What about my input value? Right, my input is also known. So in other words, if I have already chosen my activation function, what is the only thing that I can change in my activation function? No, it's not the input, right? Because input is already known. So let's actually go back one slide. Arth, yes, you're right. If you look at this, O1 and O2 are known, I1, I2 are also known. So the only thing that I can actually adjust is nothing but the weights, W1 and W2. And this right here is essentially the story of machine learning. Now, what we have done is we have explained machine learning with a single neuron, and no serious application is out there which uses a single neuron. Okay. What does weightage mean? Vignesh, I believe that's your question, right? See, Vignesh, let me give a very simple example, correct? See, when you're looking at an image, okay, say that you're looking at an image and you want to figure out if you're basically writing a program that will tell you what's the dish. For example, if someone is eating a dosa, you can take a picture of the dosa and your computer program will say that yes, that's a dosa. If it is paneer butter masala, it's going to give you the right answer, correct? Now, what are some of the inputs or features that I can identify here, right? It could be some shapes, correct? It could be some shapes that I try to recognize. And it could also be the color of the image, correct? Now, if you look at the color of the image, right? If you look at the color of the image, while recognizing foods, the color of the image might not be that important when compared to the shape of the food that you're eating, correct? If I say that you're eating something circular, there is a very good chance that you can kind of guess what that food is going to be. But if I tell you the color of it, right, it's not going to be, right? So if I'm using, so in other words, my color input all gets a lower weightage, right? So I can say that my color is not that important, whereas the shape of my food is very, very important, you know, something like that. Now, Nagashiva made an excellent point, correct? Usually, the activation function that needs to be used is not super clear, correct? People try to go with linear or very basic non-linear activation functions because those are easy to guess. But in real life, there is always a question, right? The order in which your activation functions and the selection of the activation functions helps, it's going to totally change your weights, and it's going to basically result in a different model. So a good machine learning model that one research group and a different research group creates might not necessarily come up with a new activation function. It could just be the order of operations that they take is completely different. So what do I mean by that? See, for example, this is whatever you have seen so far is just a single neuron. Now, what's the big picture? The big picture is, well, you know what? Take as many neurons as you want, right? So here I have, you kind of have to start seeing it like this, right? So this is input 1, and this is your input number 2, and you have your output 1, O1 and O2, right? What I'm doing is I'm just connecting that back to the input of another neuron. So I'm stacking up a lot of neurons. At the end of the day, I will get my final outputs here, correct? So this is what you call as the input layer, right? Because that's where the input is coming in. And this is your output layers, right? Because that's where your final output is. So what will you call all of these inner layers, right? A great name is inner layer, but usually the term that people use is called as hidden layers, right? And the depth of the neural network is determined by the number of layers you have. In general, it's okay to say that the more number of layers that a neural network has, the more capable it is. It's not going to be 100% true. There is always a question of, hey, I still have lesser number of layers, but my network is more efficient. Always have that argument. But in general, it's very safe to say that when you increase more layers, or when you increase the number of layers that you have, your model, machine learning model, tends to be more accurate. A great way to think about this, an analogy would be screen pixels, right? Whenever you have more pixels, then usually the clarity is better, correct? Can we all agree? Usually the clarity is better, right? But I can immediately give you a counter. What if you're looking at an image that's just white in color? If you're just looking at an image that's white in color, you don't need million pixels. Even if you have 5 pixels, it's going to look white, correct? But when you have now coming back to neural networks, when you have more layers, the advantage is you can basically be highly sensitive to the inputs, correct? Meaning, in the example that I gave before, where I talked about food, if I'm just using 2 features, just the shape of the food and the color of it, I have very limited number of inputs with which I'm processing my information. So that amount of foods that I can identify will decrease. But if I'm able to look at 1,000 features to determine if something is a food or not, then my model is far more complex. I will be able to try and figure out, more varieties of dishes, if my model works out correctly. Now, obviously there are drawbacks, right? Can anyone think of drawbacks of having more layers? Can anyone think of an easy, or can anyone think of a drawback that immediately comes to their mind? More time, more inputs needed. Exactly. I think you guys hit everything correctly. We'll talk about the disadvantages in the next slide. But typically, this is how your neural networks is represented. This representation is typically not used, right? Because it's a bit confusing. So you have your input layers, you have your hidden layers, and you can see that the hidden layer can have more number of activation functions than your original input layers. And then you finally have your output layers. Between each and every hidden layer, you can do additional processing. And this is where a lot of linear algebra comes into play. So if you're wondering about the importance of linear algebra, and a very common operation that's used for this is called as convolution. Okay, looks like my audio got cut. Guys, am I audible again? Okay, awesome, thanks. So let me just repeat the last point. Linear algebra is extremely important when it comes to machine learning applications. So especially in the hidden layer, one of the things that you need to do is you need to take the initial input from the input layer, which is in the matrix form, and you'll have to reduce it. You'll have to represent it in a lower dimensional form, for which a very common matrix operation called as convolution is done, right? If you do not know what convolution is, I can give a very simple example that most of you have done. How many of you are familiar with Photoshop? Have you guys used Photoshop or seen someone use Photoshop before? I'm assuming the answer is yes, correct? When you use Photoshop, one of the things that people try to do is, hey, they try to touch up their photo, right? If you have blemishes, if your skin has irregularities, you try to correct it, correct? So what do? You take the smooth tool, and what you do, then you select a radius, and then you click on your. That is a convolution. An image is nothing but a matrix, correct? An image is nothing but a matrix. And what you're basically doing is you're using a convolution matrix to multiply the image cells based upon your selection. Remember, in Photoshop, when you do the blur filter, you select your filter size, correct? You press this square bracket, and then there is a small circle which grows in size, right? That's your filter, also called as a kernel. Based on the kernel size, the convolution is done, and the final output is provided. I have a good example for convolution. I think which will come in 1 or 2 slides. Oh, actually, this is a great example of convolution. So on the top left, right, what I have is I have several squares. These squares represent a pixel. Okay. Now what I'm doing is I'm selecting. There is 400 pixels here. 20 pixels along the x-axis and 20 pixels along y-axis. Okay. So I'm taking a small kernel first, right? The red matrix that I'm taking is the kernel matrix or the filter matrix, and I'm basically taking all of it. I'm basically doing some very simple matrix multiplication, and the result that I'm getting, I'm just storing it in this first cell. Okay, so in just this single cell, I'm computing all that and I'm storing it. Now what I can do is I can move my convolution to the second cell, do it to the second cell, store it here, third goes there, and fourth goes there. This is basically called as dimensionality reduction, right? I've taken information in 20 cross 20 cells, which is 400, and I'm just representing it in 4 pixels, right? So I'm reducing the number of dimensions, and this basically helps in speeding up my entire ML model. So I'll just go back, right? Yeah, you're basically reducing the size of the blocks like zip file. Yes, but it is not. It is not just reduction in size. You're condensing information from different parts. You're trying to minimize information loss. When you use a zip file, there is no information loss, correct? But here, when you're reducing it, you can actually have information loss. That's the fine difference between what you're saying, where you are given an example of a zip file. So what's the criteria to do that? Well, that's a great question, but I won't answer that right now because that's an intermediary level topic, for which we will basically have webinars. So Varun Rao, how is data lost? Well, think about it, right? So think of this image first, right? You have an image here, and the image is represented with 400 pixels. At the end of the day, you have your image converted into just a 2 by 2 pixel, right? Just by looking at this, you cannot figure out what the original image was. Does that make sense, Varun? Awesome. Okay.